Hey everybody, hope you're doing awesome today. We're going to be hanging out in our super cool workbooks today on lesson number 6. So once again, we're thinking about what are functions, what aren't functions, more importantly, and how can we make something a function. So we're going to chat for a little bit on our first page here. Feel free, as always, to pause the video if you need to, write something good down, try something, to see if you can't figure out, is this a function or what should I do to make it a function. So use the video as we need to, or in this case, like if you need to read this first problem here. But we're talking about a function. Again, a function is just something that defines a relationship where one thing depends on another thing. Specifically, we always talk about inputs and outputs. So, hopefully by now we're realizing that when we think of inputs, we think of x values. When we see outputs, we should be thinking of y values. And if you want to be a function, you can only have one output for your input. Right? That doesn't mean that output has to be different from another input. It just means, in this case, if we have a 3 here, and we input that into our function, I always have to get a 5. Right? I'm okay if I have a 2 and I get a 5, or if I have a 7 and I get a 5. That's okay. But I can't have a 3 give me a 5, but somehow also give me another number. We'll be talking about today our functions and making function rules. All right, here's an input of 3. Our function is add 2, and we get a y, or we get a y, we get a 5. If you look here, it is written this function rule for us, right? This is the function rule, y equals x plus 2. The function rules are always, hey, here is how you get your output. You take your input and you add 2 to it. So we're going to take a look at some other examples along the way here. Maybe these couple down here will make a little bit of sense. So we're going to look at some money, some coins, which we should all be familiar with. And maybe this is a better way to think about inputs and outputs and functions. If we think of all of these coins on here, as in these are all of my inputs, right? So these are the inputs, which again are x values, right? The dollar value, this is the y, right? This is the output. This relationship that we see here, right? When I input a penny, I get 1 cent. If I input a nickel, I get 5 cents. If I input a dime, I get 10 cents, right? This relationship is a function as we see it, and maybe it makes more sense to you if I say, hey, is it possible for me to hand you a dime and it be worth 10 cents here, but maybe over here when I give you a dime, now it's worth 20 cents. Well, that doesn't make any sense at all, right? A dime is always worth 10 cents, and it can't be worth anything different one time than it is this time. And the same holds true for functions, right? They always have to be, they always have to keep giving you that same output time and time and time again. So while this first table up here with the coins represents a function, I can't necessarily write a specific rule for it, unlike I can for this bottom table. And here's why. So the top table, it's not really necessarily changing by the same amount each time. And really, if we look at our inputs, they don't, those just have names to them. So there's not like there's a pattern, you know what I mean, like there is when we look at our numbers down here. Like if we are to look at, I don't really want that. Let's there you go. If we look at our inputs, miles down here, which of course are x, calories are y, those are my outputs. If I probably, hopefully see a pattern of how am I getting from one input to the next. Well, but more importantly, we also see a pattern in our outputs, right? How are our outputs changing from each one of these numbers, right? They keep going up by 65. So, and it tells us right here, the rule is to multiply the number of miles by 65. So in other words, if I want to figure out my output is equal, or output is the number 65 times however many miles you've walked, right, or your input. So calories equals 65 times miles. All right, and that would give us. So this is a nice function rule. Is this one a function? Absolutely. Again, both of these are functions. They just look a little bit different. Let's move on to our next page. And here we're going to talk about basketball. Kind of makes sense because basketball season is upon us. So get out there and support your Wildcats. But we've got a coach, and we're going to see if we have a function. It says a coach gives each player their game jersey, and at the same time he figures out how tall they are, right? That's all up here, right, in this part right here. And it says this relationship is a function, right? And we see this relationship right down here in this table. Here's all of the jersey numbers. Right, these are all my X values. None of them repeat. Here are all of the heights, right, or the outputs. We have a couple that repeat, right? I see the number 68 on here twice, but that doesn't make a difference because each jersey number, the inputs are really what matter. None of my inputs, 10, 13, 14, 18, 21, are the same. So therefore, we have a function there. But what if we did the opposite thing? And that's what this down here shows us. We call this down here, this is a function map, right? This is a function map, as it will map your input to your output. So in other words, this says, hey, if you input a 75, you get a 14. Your output's a 14. If you input a 73, right, your output is a 13. Same thing for 74, right? You input 74, here's what you get. You get a 21. And so far we're thinking this looks like a function, but on maps it's really easy to see. Again, remember, these are all of your X values. These are all of your Y values. Maps are really nice and really easy to see if we have a function or if we don't. Because if we do have a function, all of our inputs never do what 68 is doing right here, where we have one input and it has two different lines going to two different numbers. So this one, this relationship, clearly not, all right, a function because 68 is messing that up. The other three inputs, 73, 74, 75, those were all okay. But because we see this map where 68 is going to two different numbers, that is not A-okay. Let's take a look at our data here in this table. So let's zoom in a little bit here. It says, does the data in the table show a function? Again, look at your X values. Is anything repeating? Absolutely, right? I see 3s that are repeating, right? So I see a pair of 3s that repeat, and they give me two different numbers. As well, all right, I see 5s over here that both repeat and give me two different numbers. So is this a function? As this table stands right now, no. Right? Clearly, it's not a function with very sloppy handwriting. Both 3 and 5 are causing this to not be a function. Right? And I'll say 3 and 5 give us different Y values, right? Different outputs. Okay, so not a function. However, it says if you switch, right? What happens if I switch the inputs and the outputs? So in other words, if I very quickly make a table, but I switch all of the numbers, or actually here, let's just do this. Let's switch these numbers. So let's forget, well, that's not nearly as dark as I want it to be. That's no fun. Alright, so let's just go back to this. Aha, there you go. So if you were an output, now we're going to make you an input. And if you were an input, now we're going to make you the other one. So here's going to be my inputs now. So these are the inputs. Alright, these are going to be my outputs. So now let's look at it kind of upside down or backwards. do we have a function now? So 9 and 5 and 4 and 2 and -3 are all my inputs. Well, do any of those numbers repeat? Nope. 9, 5, 4, 2, -3. Those are all fine. So if we think about it in terms of this, right? If this function, all right, if we just look at this one, absolutely we have a function, right? So let's just say yes, all right. This is a function. Again, you just have to look at your inputs and outputs. If none of your inputs are repeating, then absolutely we will have a function. Okay, let's carry on here. Let's have some fun now. Let's make some graphs. Here's our table, and it's showing us number of dog license issued in this town over a 5-year period. And we see year number 1, year number 2, year number 3, year number 4. Again, inputs are x's, outputs are y. So this is our x-axis, so this is going to be our year, right? Here's year 1 and 2 and 3 and 4 and 5. And then these are the number, right, of dog license issued. Let's just have each one of these be worth 25. So we'd go 25, here's 75, right here. Here's 125. Here's 175 and 225, all the way up there, right? And this is number of licenses. Very sloppy. So let's plot these points on our graph and see. If I just showed you this table and you looked at it, I think it looks like a function. Here's what it might look like on a graph. So here's my first point right here, 175. Here's my next point at 2 and 100. Here's my next point at 3 and 125. And my next point is 4 and 125. Okay. And then 5 and 150. All right, so here's what our graph looks like. We've got 5 dots on here. Again, x's and y's. These are my ordered pairs, right? So this, guys, just turns into the ordered pair 1, 75. Maybe I didn't make that clear. And then that's what I graphed over here on my graph. Describe the relationship between the input and output values, right? Well, the relationship is, here's your 5 years, year 1, year 2, year 3, year 4, year 5. And each one of those years has a specific or a certain number of licenses, dog licenses that were issued. So I'll let you write that in as we move down here. And we have another graph, yay, that we get to make. And this one has to deal with the age in human years, that's our input, compared with the age in dog years. Maybe you've heard of this before. Like if I said, Mr. Fricky is, I don't know, 200 in dog years, but Miss Padone is 400 in dog years. Let's figure out how old we really are in human years. So again, here's my inputs. Those are my x values. Here's my outputs. Those are my y values. So we get to graph human years over here, and we will graph dog years over here. All right, then we got to plot these ordered pairs. Again, here's your input and output. So this should be 1 and 7 and 2 and 14. These are going to be all of my ordered pairs. So if you want to take a second and graph it, you can try that on your own. Okay, so I'm going to count by, I'll just count by ones on the x-axis. So in other words, this will be 1, and here's 3 and 5 and 7. Again, these are human years. In my dog years, I might as well count by 7s. Again, this is 0, right? This is our origin right here. So I'm going to count by 7, and then 14. Here's going to be 21. There you go. Then we'd have 28. Here's 35. All right, up here would be 49. And let's plot these. So 1 and 7 are going to be on our graph. Then 2 and 14. Get that point right there. 3 and 21. 4 and 28. And 5 and 35. Do we have a function here? Of course we do. We could do our vertical line test if we wanted to. And that would, again, only go through 1 point if I drew my vertical line. So yeah, that would be a function. The relationship is just merely for every 1 human year, we have 7 dog years. And we can write a function rule for that. Maybe we will in just a little bit here as well. So let's take a look at our next page. It says the relationships on the previous page are shown in graphs. Which graph or graphs show exactly 1 output for each input? Which set or sets of data represent a function? So again, if you forgot, here's our 2 graphs. So do these show me a function? Well, I never did the vertical line test on the other graph, and if you want to, you could do that on your own, but there you go. I just did it for you. I can still draw that line, that vertical line, anywhere on my graph, and as long as it only goes through 1 point, we're going to have a function. So there's no way that I can draw a vertical line on this graph and have it go through 2 points or 2 dots on there. So I believe both of these to be functions. So let's head back over here. All right, the relationships on the previous page are shown. Yes, we know that. Which set or sets of data represent a function? I think we've clearly said that both of them do. Think about the function related to dog license. Would there ever be 1 year that is assigned to 2 different quantities? Right? So in other words, would it be possible, right, for year number 2, right, to have 2 different numbers associated with it? Well, no, it wouldn't be, right? Because it shows us right here, that, hey, year number 2, we only gave out 100 licenses. It's not like, hey, year 2 we gave out 100, and then magically somehow we had year 2 again, right? Year 2 didn't repeat. Year 2 then turned into year 3. So there's no way that we could do that. So let's write that in here. Would there ever be 1 year where that could happen? No. I'll just say that isn't possible. Right? Because again, the next year would have its own number. You couldn't have 1 year you somehow gave out 2 different amounts because we're including everything in one. Look at your answers to problems 3 and 4 on the previous page. So again, we're still thinking of those 2. Can either of those be written with an equation? Right? So could we write dog years in an equation? Could we write the number of license issued? All right, let's take a look real quickly. We might as well just write them over here while we're here. Let's start with the dog years one really quick. So again, is there a way for me to write, hey, the number of dog years is equal to the number of human years? And yeah, if we look here, right, we see this is kind of some 7th grade math, like unit rates that we would see. So I would say, yeah, y equals 7x here. I just figure out how many human years you've been around. So for Miss Padone, that's a really large number. We won't mention what that would be. But then we'd multiply it by 7, and that would give us how many years in dog years you would be. All right, now can we do that for the other one? Right? Can we do that for the other one up here? Right? So is there some pattern, is there some relationship between basically each one of these ordered pairs, right? Between 75 and 1, and between 100 and 2, and 125 and 3, right? I would say no, because it's not like the other one, right, that we saw down here, where I can just take the output, right? And if we do a little bit of division, so if I took the output and divided it by the input, 7 divided by 1, that's 7. 14 divided by 2, 7. 21 divided by 3, 7. Right? That's where that 7 comes up from. But if we look back up here, as I struggle to navigate, 75 divided by 1 would be 7, but 100 divided by 2 would be 50. Right? 125 divided by 3. Okay, we're not getting the same number. So no, I can't write that one as an equation. All right, and that's our answer to number 8. So yes, we can write the dog years. No, we can't write the number of license issued. Okay, inputs and outputs. So now we're going to fill in an X and Y table, right, or this input-output table, based on the following rule. So here is my rule, right? Your output Y is equal to your input plus 2. So in other words, I'll just start here at 0. If I start at 0, and that's my input, and I add 2 to it, well, then I end up getting a 2. Right? If I take 1, I add 2 to it, I get 3. 3. It could be the worst 3 I've ever written. Oh my goodness. Go away. Let's write a better 3. Sweet. We get a 4 here. We can do negative numbers as well. Negative 1 plus 2. Just going to be 1. Negative 2 plus 2, 0. Alright, I'll let you think about that. Is that a function? Is that not a function? Let's fill in the table on 10. Again, the function is y equals 4x. So again, I take my input, negative 2, multiply it by 4, I get negative 8. Alright, here I get negative 1 times 4, negative 4. 0 times 4. Alright, 1 times 4. And 2 times 4. Okay, so let's study those. If you want to pause the video, you can. In the meantime, we will answer these questions. State whether each equation represents a function. Yes, both of these do. Alright, and I'll just put on here, if there is no exponent, alright, in the function, alright, we will have a, it's really not great grammar here, but if we don't see an exponent in our function rule, chances are very, very, very overwhelmingly good that we're going to have a function, and we see that in our X and Y table. Look at your inputs. Do any of them repeat? No. Right? Look at our outputs. The outputs don't matter as much because we don't have any of the same inputs. Here we go. Looks like we got a function map, and we're going to do something with this. Here it wants us to take our function map and take all these numbers that we see. Right, we're going to see a whole slew of numbers right here. And it wants me to put these numbers into my oval so that I do have a function. And it's already given some of these for me. Right, like here it's already used negative 4 and negative 3, 1 and 2 and 5. Right, it's already used those for the inputs. For the outputs, it's already used negative 3 and negative 1. So the only numbers left for me to fill in really are 5, 6, and 7. And it doesn't really matter what order we put them in. We could just say, hey, here's 5, 6, and 7. And, you know, I could say, hey, 1 goes here, 2 goes to the 5, 5 goes to 6. And we've made our map, and everybody's happy. But now it wants me to make a second one. But it wants this one to be a function as well, right? This one on the left is a function, so I need to make one on the right here that is also a function. But be careful, we've got some numbers that repeat in here. Like I see a pair of 5s. I also see a couple negative 3s. So think about what that does for inputs and outputs. So if you want to pause this, you can. If not, I'm just going to pick some numbers here, and I'll make my own. There's many, many, many combinations that we could have, but I'm going to put negative 4 here. And we've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers on here. So I'm going to say -4 and -3. I'm going to skip the other -3. I'm going to go with -1 and 1 and 2 and 5. Alright, so let me cross these off so I remember that I used them. That's gone, and that's gone, and 2 is out, and 5 is out. Alright, and so here's what I'm left with. I'm left with these other numbers. So here's a -3, here's a 5, here's a 6, here's a 7. Notice I have more inputs than I do outputs. That's A-okay. There's nothing wrong with that. That just means we're going to have one or more inputs that go to the same output. And like I said earlier, that's okay, right? I can have -3 and I can also have -1. Both go to 5. That has no bearing on whether or not you get to be a function, right? 5 can also go to 6. This is still a function. So we're good with that. I'm going to let you guys try to tackle number 12. Then I'll give you my answer for that. So we'll go ahead and pause this. Okay, so if you've read through number 12, it says a bag includes one number card, numbers 1 through 25. And then we have 25 students. And if each one of them picks a number card from the bag, would that be a function, right? So the answer to this one is yes, it would be, right? Both Carrie and Mario are both right. Carrie says, hey, if the number is the input and the student is the output, it's a function. Yep, that would be true. Mario says just the opposite. He says if the student's the input, the number's the output. But remember, I have the same number of students and the same number of cards, and each student is getting a card, and it's not like they can be repeated at all in this scenario. So yes, they're both right because they're both functions. On 13, go ahead and fill in this table, right, and see if we can't figure out if we have a function here. Okay, hopefully you're back. It says each molecule of water contains 2 hydrogen atoms. Again, inputs X, outputs Y. So if I input a 1, right, I have 1 atom of oxygen, I have 2 hydrogen atoms. Here we go. If I have 2, I have 4. If I have 3, I have 6. If I have 4, I have 8. It says, is the number of hydrogen atoms a function to the number of oxygen atoms? Absolutely, right? If we think about this in terms of a function rule we could write, we'd have y equals 2x. And clearly this one's a function. Every input has a unique output or its own output. We see that through this table. All right. And finally, guys, we made it. Woo! Last page. Last page, you guys are going to do a little bit on your own. I'm going to give you some help with A, and then I'm going to turn you guys loose. So A, all of this actually hinges on whether or not we can write a couple of function rules for Sean and Rachel. All right, and here's what we know. They were both born on April 17th. When Sean was 4, his sister Rachel was 2. So write an equation that can be used to determine Rachel's age, given Sean's age. So in other words, if we said that Rachel is R, so Rachel's age has to be equal to Sean's age, right? Rachel is 2, Sean is 4. So how could I, if all I knew was Sean's age, how could I get Rachel's age? Well, I would take Sean's age, he's going to be S, and I'm just going to subtract 2 from it. Right, that makes sense. Right, Sean was 4. 4 minus 2 is 2, and Rachel was 2. So there you go. All right, so there's Rachel. Let's draw a squiggly line here and do the opposite. So if I want to figure out Sean's age, but I only know Rachel's, what do I have to do? I've kind of got to do the opposite of what we just did here a second ago. I need to take Rachel's age, and I need to add 2 to it. Right, if Rachel was 2, Sean was 4, so 2 plus 2 gives me 4. So I'm going to let you guys go on the rest of this. Go ahead, fill out the table, right? It's giving you all the inputs you need. Then describe the relationships you see. Are they a function? Are they not? And then you've got one last question on there, question D. So apologize for the super long video. You guys were so attentive. You guys are great. So hope you're having a great Friday, and we will see you next time.